Well, I think we can start officially. Welcome back, everyone. So we're nearly done with section 4.1. After that one's complete, the longer section for chapter 4 is going to be this section 4.2. We'll probably spend a couple days completing that section, and it should be done sometime this week. After we're done 4.2, we're going to start to change gears, go to chapter 5 to start talking about probability theory. We only need as much probability as it takes to understand how to do a hypothesis test, how to deal with a confidence interval. And if you're more curious about what in the world we're doing with probability, it's all about this right here. This is our major problem we have at the moment. We know how to define a population, how to select a sample. And once we have a sample, we can calculate statistics like the sample mean X bar, the sample standard deviation S, or other statistics. And this right down here is our ultimate goal, to display the parameter mu is approximately equal to whatever the sample mean is. But in order to determine how worthy that estimate really is, the error in the estimate, the accuracy, we have to deal with probability. So that's the major reason. Well, we'll be turning to chapter 5 once we're done with our section in 4.2. Let me see if I can bring that back. There we go. Well, it wasn't quite there. Like that. So that's where we're at and where we're going. Any questions at the moment, folks? Okay, I also put here, just because it says midterm week, the reminder is there's no actual exam for midterms in this particular class. All we'll be doing in midterm week is, I'd say probably on Friday of that week, I'll pull your grades from the homework, your quizzes, and the one exam that we had, put them together. I mean, you can see what it looks like right now. Go under grades right here, and your course grade will become your midterm grade. Really, it's just an opportunity for us to report in the middle of the semester where you're at right now. Any questions, folks, about where we're at or the midterms or otherwise? Okay, aside from midterms, if we go up to the further future, let's see. Exam 2 is going to be held Monday, October 16th. So still quite a ways away. I mean, it's not even October yet. But once we're towards the end of this week right here, I'll start putting down the information for exam 2, review materials, and the same kind of things we did for exam 1. Well, I think we're ready to get started, folks. Any questions at all before we jump back in? Okay, well, back to section 4.1. We almost finished it, but I didn't want to try to rush through the last 2 questions and go over a few minutes trying to get through it. So here's where we ended up in section 4.1. We were looking at this example here, where we have the 13 best paying US companies. And amongst those 13 top paying companies, they recorded 2 numerical variables. So for this bivariate data set, that we have median worker pay tied together with the percent change in stock price. So for example, if we look at just a random row here, I have no idea what that company is. Folks might know. Anyone happen to know what Xilinx is? Apparently in 2015, that was a top 13 company in the United States. Never heard of them, but their median worker pay was $121,000, and their percent stock change increased by 5.2% in that year. So what we did with these data is we treated X as the explanatory variable, Y as the response variable. We produced a scatter plot, and here it is. In that scatter plot, we finally were able to use our rule of thumb, calculate the correlation coefficient, came out as 0.58, and we were able to say that the relationship we see here is moderately strong. The reason we said moderately strong is based off of this scale right here. Well, that takes us to finally where we left off on these data, part C. But first, any questions or comments with what we've done so far? Okay, so what we said in part B, after we calculated the correlation coefficient R, drew on this regression line here, is that there's a moderately strong positive relationship between the median worker pay, that's the X variable, and the percent change in stock price, that's the Y variable going this way. So in other words, the more the employees were paid, the higher the stock price tended to be. With that in mind, here's where things go a little bit wrong with this. Part C says, the article states that companies that pay more are seeing a payoff in their stock performance. is this conclusion justified based on the data? Well, it turns out that conclusion is not justified, and it's really kind of subtle to see why. Anyone see why this is the wrong conclusion? Not necessarily the strength of the association. It's really kind of a tricky last couple questions here. And they're really sort of review questions in a certain sense. While we think about this, let's turn to chapter 1. It's kind of a nasty question in that sense. We go all the way back up to chapter 1. What we needed is this section 1.5 to help us with this question. So we had this good old table here way back in the day. I think this was like still week 1 of the semester, maybe week 2. But there's 2 kinds of conclusions you can make based off the study. Either you're going to generalize the results from the sample to the population, or you're going to make a statement to add cause and effect. So any kind of statement that's in the conclusion that sounds like cause and effect is a concern if your study was not a controlled and designed experiment. And this one wasn't. We have 13 of the top paying companies, but we didn't split them into a treatment group and a control group. There was no placebo. We just observed the data that was already there. That means this was an observational study, and any conclusion that even hints at cause and effect is just completely off of the table on this. So going back to 4.1, they're saying companies that pay more are seeing a payoff in their stock performance. That's a dangerous statement to make. It seems that they're saying the more that employees are being paid, the higher the stock market went. And we see that on the graph, but what we have to say is higher payment for the employees is associated or is related to higher stock change or stock price performance. So let's write this out really carefully. Part C is not something that's actually in the homework and website, but again, it's kind of a review question all the way back from chapter 1. We'll say here, is the conclusion justified? And it is a no. Put an exclamation mark on there. To explain it, we'll say, this conclusion is suggesting, and we can't even suggest cause and effect, but it is suggesting that higher pay, and let's put this word here, causes higher performance in the stock price. And that may be true, but again, if we want a conclusion of cause and effect, we have to design an experiment in order to get that conclusion. So if we have that they're suggesting higher pay causes higher performance in the stock price, we'll say here, this was not an experiment. And so we cannot make a cause and effect conclusion. Cause and effect conclusion. Oh man, that's a long sentence that turned into. Let me try to fix that penmanship. The Microsoft document just gets really angry at the boundary of the page. Cause and effect. Sorry, I deleted a bunch of words. Experiment, performance, suggesting. I should probably just Control Z this, try to bring it all back. Sorry, some weird issues with Microsoft Word. Okay, I think we're in better shape. Conclusion. Okay, finally got it all in. So that was the danger with this statement right here. Any questions or comments at the moment? Okay, I wanted to add something extra to the notes here. What should the conclusion have been then? If this conclusion, companies that pay more are seeing a payoff in their stock performance, cannot be made because they never actually devised an experiment. What conclusion could they actually make? It might look like this. I'll put it down here typed out. It's not our official response, just extra information. They can conclude that higher pay, let's put this in italics, is associated with better stock market performance. So if you ever wondered why some articles like to talk about associations in this kind of way, that's what they're trying to get away with. There is an association between the variables. The correlation was moderately strong. And even if it was weak, we'd say we have a weak association, but that's never an association of cause and effect. So here, if we make this statement and we're really careful about it, then that is an okay conclusion that could be made. Let me put here, this conclusion would be correct. This is a correct conclusion. Well, you did it, folks. This part C right here is definitely a really tricky question. Does it make sense to everyone what the issue was and how we got around it? Awesome. And that's kind of the danger with multiple variables. Even if we're dealing with, say, two numerical variables like this, even if the correlation was really weak and instead of moderately strong, we always have to pay attention to, was it actually an experimental design or not? Well, that's the issue with part C, and there's another issue in part D. Part D asks, is it reasonable to generalize the conclusions based on these data, think of the correct conclusion now, to the population of all companies in the United States? In other words, if we think of those 13 companies as a sample, can we generalize these results to every company? How do folks feel about that statement there? Would it work, or do we have a problem? Some are saying, shaking their heads, this doesn't seem like it's a good situation. Anyone see what's missing that would allow us to generalize the results? Yeah, go ahead.
I think it's not random because they just chose the top 13 highest paying companies.
Exactly. That's the whole problem with this. Even if we're only talking about well-paid companies in the stock market, still not random if we take the literal top 3. There's no randomization there. That's an actual strategy or a structure to the sample. So if we go back to this graphic right here, this is also extremely required for us to generalize. Generalizing the results of the population is similar to making that kind of a statement here, using the sample data to conclude something about the underlying population. But like you mentioned, let's go to the top of the problem. This was not random. It was specifically the 13 top paying. And so the only conclusions you can make here are about these 13 companies and none of the others. So let's say that really carefully down below. We'll say no. These data did not come from a random sample. So again, think of part C, part D, kind of just review information, things that we talked about in chapter 1. Occasionally, these will be sprinkled into the course, just so we're reminding ourselves of these issues. But once we get into chapters 8, 9, 10, and 12, those are going to be things we talk about all the time once we're actually doing inferential statistics. But we did it, folks. That's the end of section 4.1. So in a certain sense, we're halfway done with chapter 4. Any questions before we go to the last section? Okay, let me save this up. And the punchline to the last section is we're going for that line there in orange. We want to see how to produce it, how to work with it, make predictions. So I'll save this up. We'll take a small break while it tries to save this. And here we are finally in section 4.2. Let's take a tour of the notes just so you can see about what's going to go down on here. The first example 1, it's really not statistics. Think of this as just a warm-up. We're just getting used to dealing with lines. Then when you get to here, this is going to be my attempt to explain what do we even mean by least squares regression line. Everything that happens on this page right here is highly formulaic. But as you know, our calculator is going to do most of this work. So these are here just for information to see what's going when we calculate a least squares regression line. So I wouldn't put any of this on my notes for an exam. I wouldn't try to memorize it unless you're curious and you want to, then go for it. That's a great thing to do. But once we hit example 2, now we're doing the problems like you'll see on WebAssign, quizzes, or exams. So we'll do a couple of these kinds of examples on 2 and 3. First, we'll start here, just getting familiar with lines because that's the whole thing we're doing here, coming up with the least squares regression line. Well, here, our line is written in a weird way. If you just came out of math class, say like intermediate algebra, college algebra, or otherwise, you probably drew your line like this, y equals mx plus b. Excuse me, wrote down the equation of your line. Or you might have wrote your equation like this, f of x equals mx plus b. But in statistics, for one reason or another, people get in the habits of writing their lines differently. It's written this way, a plus bx. Kind of unfortunate, but we can work with that. That a right here is going to be the y-intercept. This is what the y-intercept would have been in a math class. And this b you see right here, attached to the variable x, that's going to be the slope, which we would have called m in another math class. So here, the value b being the slope right here, is going to tell us the amount. The dependent variable, the response variable, will increase or decrease whenever x is increased by 1 unit, where x is the explanatory variable. And the intercept, that's just going to be the value that y takes when x is set to 0. Well, any questions, folks, with the definition here? Okay, so this is our slope-intercept form of a line. And what we'll do right away is just practice plotting with this just to get a feel for it. So right away, we want to make one observation, that this quantity is the slope. It's attached to the x variable. And this quantity will be the y-intercept. Now we're going to go to a graph just immediately. The instructions say plot the line. And anyone know what first point we have to put down, where it would be, what number it would be? If you're not sure, no worries. It's kind of the reason we're practicing right here, just to get everyone on the same page. And just to allay any fears, there'll be no actual math questions on any quizzes or exams or WebAssign. This is purely just so we could get some practice before we get into examples 2 and 3. But the way we would start this off is, let's put down a sequence of steps. Step 1, we take the y-intercept. The intercept is -5, so we'll say a equals -5 is the y-intercept. I'll usually write y-int for shorthand for y-intercept. We'll go down on the y-axis, 1, 2, 3, 4, 5, and it goes down into that location. Let me put a little bit more description here. This is the y-axis, and this is the x-axis. So that takes us to our very first point on the line, way down here. If this was, say, a +3, we would have gone up 3 tick marks on the y-axis, and that would have been the first point on our line. Make sense so far to that stage? Okay, well, step 2 then. We're done with the y-intercept. Now we use the slope. Usually we call slope m in a math class, but in statistics, everything is a little bit backwards. We're calling the slope b. So b in this problem is 7/3. And think of this as instructions or an address to get to the next point once you've already put down that point over there. What it's telling us to do is, let's get a pen going. We need to go up 7. I think an arrow looks better there. If that was a -7, we would have gone down 7. And here we'll go right 3. So up 7, right 3 from where? It's always from what you did on step 1, the location of that y-intercept. So let's visualize doing those instructions. First, let's go up 7. That'd be 1, 2, 3, 4, 5. 5 takes us right to the origin. And then 6, 7 will end up at this height right here. But then we have to move to the right by 3 units. So this will be 1, 2, 3 units to the right, ending us up into that location right there. I'll put this in green because we got it to that point by using the slope to get there. Finally, for this entire line, the whole equation, well, because it's a line, 2 points will specify its graph. And here's the hardest step. Draw a line through those points to the best of your ability. If you miss one, just make the point a little bit bigger. That's our standard strategy. And that's finally our official line for -5 plus 7/3 x. Well, any questions at all, folks, on getting to that line there? Okay, now that we have that line, let's call this a part A. Now here's something that we will do once we have a line produced by a calculator. Let's say for the instructions on B, evaluate the value of y when x is equal to, let's say, 6. Why not? So sorry, that's a brand new problem right out of the blue right here, but this will be helpful for us as well once we're dealing with the regression line. So we want to find out what is the y value when x is set to 6. All we'll be doing is placing a 6 right there where the x is, and we'll get this as a result. Y equals -5 plus 7/3 times 6. Then you can work this out step by step using arithmetic if you like, but also keep in mind, you have a calculator, so you're also welcome to compute in this way, which is probably what you would do in example 2 and 3, including WebAssign. I'll just go -5 plus 7/3 times 6. And that gives us the value of 9 altogether. Double checking, if we did this by first principles, 3 cancels into 6, leaving a 2, times 7 gives us 14, -5 would take us down to a 9. So we get a value of 9 on this problem here. Well, any questions at all, folks, on running through these? Okay, our purpose for doing all this is, once again, the calculator is going to give us the equation of the line. We're going to freehand sketch that equation. But it's good to know what it looks like, what each of these portions actually do for us. And we will do something like part B. Once we have the line, picking a value for x and getting the y value out is us making a prediction once we already have the line itself. Well, let's now try to take a look at what is the least squares regression line. Any questions or comments whatsoever before we go to that wall of definitions? Okay, so here's how the least squares regression line is finally defined. I want to zoom in just to right here. Let's focus on this definition and that graph down below. So our goal is to fit a line, y equals a plus bx, to all these dots right here. In fact, let's do this right now. If we use just our eye and try to fit that line, again, people are actually pretty remarkably good at this, but getting the exact line that performs in the most optimal way, we do need to have a formula and a method for it. So this line might be pretty good. And software will get that in much more exactly. So that's what we're referring to by the line y equals a plus bx. Let's call this y equals a plus bx right here and start working with this line. So we're fitting it to bivariate data, which means all of our data comes into this form, a pair of x values and y values all together. The x values, let me click right over here, are what we have on the horizontal axis, and the y values are what we have on the vertical axis, like before. So each of one of these is a point xy. X1, y1 is just saying that would be the first point. X2, y2 is the second point. All along till we get to the last point, which we'll call xn, yn. Let's maybe focus on this one. Let's call it our first point. This is x1, y1. And the thing that we're trying to optimize to make this line the best it could possibly be is these vertical distances. There's this separation between the actual data value we had, which is in green, and the value that would be on the line. The value on the line right here would be the predicted value that's coming out of the equation, y equals a plus bx. We're seeing that equation right here coming from that point, and that's what you're seeing right here, a plus b x1. If you plug in the x1 inside here, that's exactly what you're getting. What's the y1? The y1 is this coordinate. We go horizontally to the left. That's the y1 value right there. So when we take this subtraction, y1 minus a plus bx, follow the highlight to see which is which, we produce this difference right here. That's exactly y1 minus a plus bx. We're going to square that so it comes out positive, and then do that for every single point on the line. Some of these have very small distances that we're squaring, say around here, right around here. The values are very, very close to the line. But not every one is. This point right here has a large difference between the actual value and the predicted value on this line. But nonetheless, we keep on calculating all of these differences. Let me put them on the chart here. So imagine you're taking all of these red line segments, squaring them, the lengths of them, and you're producing this right here. Well, that's a lot going on, but here's the big punchline finally. The least squares regression line is the line that's going to minimize the square of all these lengths in red. In other words, it minimizes all of these differences right inside here. There's exactly a unique solution to that. That's remarkable on its own. Once you find this line, that is the only line that will make the square distances here in red as small as possible. It's in that way we call this the least squares regression line. And if you think this kind of stuff is cool and fun, ISU offers an entire course called Least Squares Regression Analysis. So this is a kind of topic that just can go for an entire 16-week semester. And depending on your program, you might have to take it anyway. So think of this as kind of the introductory topic to that field. Well, how you actually calculate the least squares regression line is different from how it's defined. This is just the definition. To crank it out, I copied this out of the textbook just for folks that are curious. It takes quite a lot of work to really come up with it. The formula for B is that thing, that's the slope. The y-intercept, it doesn't look bad, except it does involve B, that thing right here. And finally, the least squares regression line, we typically write in this format. Notice the thing that's a little bit odd about it right here. There's a unusual symbol on Y. There's the so-called hat symbol. So this is read as Y hat. Whenever you see a symbol like that, what it's saying is Y hat is the predicted value. So we often write our least squares line as a Y hat. That's not a requirement in this class, but it's a pretty good habit to get into, especially if you know that you're probably going to be doing more statistics, more regression. Well, that's the definition. This is the nuts and bolts on how it's cranked out. The calculator has this all programmed in as a routine, and so we'll be taking advantage of the calculator rather than using the formulas directly. This would literally take all day, possibly all week, to do a problem from scratch if we had to calculate every single object by hand. But computation allows us to focus on the concepts without getting bogged down. Next thing we're going to do is actually apply this and calculate to one of these lines right here. Any questions at all, folks, before we get started? Okay, here's our first official problem like you'll see in WebAssign, quizzes, or exams. We're going back to the algal blooms or algae blooms. We didn't have a lot we could do with this data when we first looked at it because we were only just getting started. But now we can go through this and complete it. Let me fix that right there. Let's first remind ourselves of the context because it was a number of days since we've seen these data. So we're looking at algae blooms. In certain areas, they have a very nasty effect on ecosystems. They can cause algal blooms that can wipe out all the oxygen in the body of water, thereby just annihilating all the fish and other nasty things it can do. And so in order to control these particular algae, this particular, I'm not even going to try to pronounce that scientific name, this is what they did. A research team examined the relationship between the net growth rate of this algae and the number of these things. These are what eat the algae, thereby hopefully controlling it. I'll just call them the grazers. They're introduced in the test tube. So remember, a net growth rate is negative, meaning a decrease in abundance. More negative means that the algae was feasted upon even more by the grazers, and we expect it to be reduced even more the more feeders you put in, the graders in the test tube. So these are the data produced as a scatter plot. And it says right away, calculate the least squares regression line, then plot this line on the scatter plot above. So we're in business, folks. We're finally going to calculate that line. First thing we do is power on the calculator. Immediately just hit stat, and we're going to import these data right here. The explanatory variable from last time we did this problem is number of grazers. So think of this as your X variable. Your response variable is net growth rate. So this is Y. And an even further reminder is your X variable, you ought to put it in L1 just for the sake of consistency. And for Y, put it in the L2 column. So now I'll hit enter here. Let's clear out all these data from, I guess this was last class. And now the data import. I'll do grazers first in L1. So 1, 2, 3, 4. Then you could go right arrow and now put in the values for the net growth rate. So negative 1.9, negative 2, oh, negative 2.2, negative 4.1, negative 4.3. Okay, with that data in, if this were a web assigned problem, I would probably double check those numbers. This is again another one of those kinds of questions where if I in fact made a mistake, call this negative 2.1 right here, that's enough to lose the whole question. So data import is maybe the trickier step about this. Once we have that all in, hit the stat key. We're going to go over to calculate. And here's a reminder, we're not using option number 4. Sadly, the only reason we're not using option number 4 is because our author does her lines like this, A plus BX. If we use option number 4, we're going to get the wrong A and the wrong B. They'll in fact be flipped on us, massively confusing. So scroll down to option number 8. If it goes A plus BX, you're matching up this right here. So now you're speaking in the same terms that we're all saying, and you won't have your information backwards. Okay, so we imported the data. We went to calculate all the way down to option number 8 and hit enter right here. In fact, hit it a bunch of times. And this is the output that we're going to get. Gives us a lot of stuff. If you have your diagnostics on, it'll give you the correlation coefficient R. R squared is the coefficient of determination. If you take more statistics, what R squared is telling you is that 88% of the variation in these, the way they're jumping up and down, was explained by the number of grazers. So that's almost all of the variation by that one single variable. But what we need is this right here, the A and the B value, so we can put it together as an equation. So I'll take a screenshot of the calculator just so that if you come back to these notes to study or practice for the homework, this is how I'm answering this question or where I'm going to in the calculator. The answer is going to be in the format of y equals A plus BX. And let me remind myself of how this is color coded. Okay, blue and then green. Just don't want to split that on us in the middle of the problems. Also, I'll put a hat on it just to remind ourselves that's the predicted equation. Then we go to the calculator and just write them out. So y hat is going to be a first, negative 0.85. Then it'll be plus a negative quantity for b, so I'll just go minus 0.91 times x. I'll put a box on this just to emphasize that's the official answer we're going for this kind of problem. It's not enough to know the a coefficient or the b coefficient. When it asks for the least squares regression line, it's got to be all of this right here. Well, any questions, folks, with that computation here? Okay. Next thing it says is plot this line on a scatter plot above. But this is what I encourage you to do. Definitely don't overthink it. If you put a line that goes like this, the line that just seems to fit it the best, I'm always okay with that. You don't have to plot your line precisely. That's okay if you just do this. Because in the end of the day, this line, if we did try to apply precisely, is probably going to be pretty close to what we put here anyways. I wouldn't be able to tell the difference. Well, we have the line there, we have the full equation, and now we can finally work with this and ask and answer questions about modeling these algae and how their growth rate is affected by the grazers. So that was the major thing we wanted to get through. Now we'll be working with this equation here. Any questions at the moment? Okay, I forgot to ask. Anyone have any trouble getting this out in their calculator, or is it being produced all right? Okay, glad to hear it's working out. If you have any questions doing this in WebAssign, if, for example, it's just not taking your answer, please don't hesitate to hit the Ask My Instructor button. It could be something like a rounding error, or maybe sometimes when I put these in the calculator, I might put in a negative 4.2 just on accident. Your results will be very, very close, and I'll be able to tell that. So if your answers are really close, I'll assume it's a simple mistake or a rounding error, and I'll help you out to just tell you what the answer is. So don't let yourself get kind of just really upset at your computer, smash a keyboard or anything like that. If WebAssign gives you trouble, please don't hesitate to hit Ask My Instructor. Well, let's go off then to the next portion, part B. It says give a practical interpretation of the y-intercept of the least squares regression line using the context. I'll highlight this in yellow. This is a reminder when it says using the context, you have to be talking about the number of grazers and the net growth rate. In fact, I'll take a quick screenshot here, just as a reminder as we go through this question. Well, to get through this question, we also have to know what do they mean by the y-intercept. And the y-intercept is this value here, the negative 0.85. So that's what we're interpreting. If we look at the notes on the y-intercept, the way you get the y-intercept as an output is you have to plug in a 0 for this x. Let's do that right here. At x equals 0, y hat is going to be equal to 0 goes inside there, so it's just a negative 0.85. Let me put the red dot where I'm looking. Negative 0.85. And then I'll just go minus 0, because that 0 is going to wipe out to the 0.91 since it's multiplying. And so we get to negative 0.85. So if you ever forget the formula for the y-intercept, just plug in 0 for x, and then you're in really great shape. This is a good strategy for two reasons. Sometimes the y-intercept has no meaning in a particular problem. Other times it does, and you just have to decide, would it make sense to plug in a 0 for our particular data? Well, that depends on what x is, right? X is the number of grazers. And yeah, you can have a test tube in this experiment with no grazers, and we're just looking at what happens to the algae. That's something they maybe should have done just to get a baseline, for example. So we can say here, let's now give a practical interpretation when the number of grazers is 0. I pulled that from this right here. We picked it 0 to get our y-intercept. The net growth rate is that value, negative 0.85. So that's our interpretation of an intercept in this kind of context. This is a pretty tricky problem. Webbicide gives us kind of an upper hand because it's multiple choice, but then we have to know how to do it on a quiz, and we have to know to do it on an exam, just running through it on a question like this. So think of Webbicide as the warm-up, and this is what we're going for right here when this question comes up again. And we have another example on these notes. We definitely will try this again. Any questions or comments at the moment, folks? I guess I have a comment. You know, what makes me feel weird about this one is the net growth rate is still negative, even when there's nothing eating it in the test tubes. But that might make sense only because, remember, this is a specific algae that they grabbed out of the ocean or a sea somewhere. And then when they put it in a test tube, it's not thriving, it's slowly dying. It just happens to be dying faster when you put things inside the test tube that's eating it as well. So that's what's going on here. And now we're going to do another interpretation, this time for the slope, the negative 0.91. Any comments at the moment before we change gears to the next part? Okay, so let's go to that slope next. We want another practical interpretation. This time it'll be for the slope. And we have to use the context once again. The context, it gets a little bit easier the more and more we practice with it, but context just means if the study is about grazers eating algae, we have to say that somewhere once we go to write this out. So now in part C, we have a slope of negative 0.91. And we need to interpret that value right there. This is actually kind of tricky. And there's a whole setup for doing this that goes kind of like this. First thing you want to do is convert your slope into a bona fide fraction. Any number, even if it doesn't have a denominator, you can force one in. You can give it a field promotion by dividing by 1. So our slope is now this. The next thing I'll do is give it units. Now here's the next trick. Let me get a better display here to help us out. Here's the line that we drew on it, roughly. Now, when it comes to a slope, the slope is measuring a rate of change of your horizontal axis against your vertical axis going this way. So it says if it's negative 0.91, any point we pick here, let's say we pick a point right here, if we move over by 1 unit, that's this portion where we divide by 1, we have to go down by this amount, negative 0.91. So that's enough to tell us what the unit should be. If in the denominator we're going right 1, that means we're increasing the number of grazers by 1. So I'll put down below 1 grazer. Next, if we're going down by 0.91, that means our net growth rate is what's going down. So that's going to be the unit in the numerator, negative 0.91 net growth rate. So let me put down a step on this one. I would call this step 1. And it's a very, very good idea to do this step 1. If you omit it, I wouldn't take off points. But to get the actual practical interpretation and really using the context, it's a bad idea to ignore step 1. Definitely rewrite your slope, throw in the units, and then this is what the practical interpretation will look like right here. Let me write it out really big because this one again is kind of tricky. It goes like this. I would start with the denominator and say, as the number of grazers in the test tube increases by 1, That's here where we're going right one. We're increasing the number of grazers by one. Then something happens to the growth rate. We can say the net growth rate. Let me make that look like an actual letter T. There we go. The net growth rate is expected to decrease by 0.91, the value of the slope in this problem. So that's finally our full interpretation. Now notice I put in 0.91 without the negative sign, and that's because I already mentioned negative right here when I said decreased. If I said decreased by negative 0.91, that's double negation. You're saying it's actually increasing. So writing it out in words is a little bit weird because of those issues there. Well, we did it, folks. It's really just interpreting an ordinary slope, rise over run, but pulling in the context all at the same time makes it kind of a tricky question in all honesty. Any questions or comments on getting through this one? Okay, well, we've done it, folks. That's interpreting the slope right here. Now, word of warning, the slope doesn't always make sense in interpretation. We'll see that on the next problem. Or I said that backwards. Let me start over. On part B, we're dealing with the y-intercept where we set x to 0. But setting x to 0 doesn't always make sense. Like we'll see in the next example. Here it did. But when it comes to interpretations of the slope, there is always a practical interpretation, as long as there really was a relationship between the variables. And for the next part, let me take a screenshot of this right here. I'll leave this graph right here as part of the explanation of our strategy. Let's hide that example. And here's our final problem for this example too. It says, calculate the predicted net growth rate for 2 grazers. Essentially what we're doing right here is the same of what we did here. We put down a line and we said evaluate it when x is 6. For us, x is 2 because they said 2 grazers. So back down to this problem. Here's how this one goes. It's really just a calculator situation. Predicted net growth rate is y hat. It goes negative 0.85 minus 0.91. And inside here, we put in 2 grazers in place of x itself. So throw in the 2. We're going to now just take the calculator and crank it out. And that will be our predicted growth rate. So negative 0.85 minus 0.91 times 2. Can throw into the calculator, pretty much just typing out verbatim like on paper. And the predicted net growth rate is negative 2.67. So we did it, folks. That's working with this equation here, and we even made a prediction. What's kind of interesting about this prediction, though, is we were predicting on 2 grazers. The data is already right here. At 2 grazers, we had this value. It looks like negative 2.3 or 2.25. We found negative 2.67, and that is about, I'd say, here. So the real data is in yellow. What we calculated at y hat is just a little bit lower. We should expect that. Each time you run an actual data value through this kind of equation, it's not actually going to give you the true value back, because this is the real picture with the least squares regression line. Typically, the line misses every point in its effort to try to get as close to as many points as possible. So that's what we saw happen on this one. At 2 grazers, we should have gotten negative 2.2, but there's error in that prediction. It came out as negative 2.67. Nonetheless, it's still a valuable equation, and we'll do other kinds of predictions on the next example. Any questions or comments at the moment, however, before we call it a night? Okay, that's a pretty tricky problem. And so what I encourage you to do once we go and finish off this example, if next class you feel like we need more practice after example 3, let me know. I won't have any trouble coming back with an example 4 to go along with these notes, just to get some more practice in, because I'd say this kind of territory is definitely different than anything else we've done so far. Well, have a great night, everyone. I'll see you all in Wednesday's class.